Okay, hi folks. We're going to get into the kinetic model of gases. And so this is kind of another way that we can start to look at gases in an idealistic way. And the kinetic model of gases, or sometimes referred to as kinetic molecular theory, assumes that the only contribution to the energy of the gas is from their kinetic energy, so the way the molecules are moving around. So we start by noting the three postulates of KMT. The gas consists of molecules of mass m in ceaseless random motion obeying the laws of classical mechanics, so Newton's laws. The size of the molecules is negligible. Their diameters are much smaller than the average distance traveled between them, between collisions. So we could think of each molecule as like a little point-like molecules. And the molecules will only interact with each other through brief elastic collisions. So we assume they don't have any type of intermolecular forces, and those elastic collisions follow that of classical mechanics. So they bounce off each other and bounce right back. Okay. So one of the aspects of KMT is the Maxwell-Boltzmann distribution, which we already derived. So let's write that down, Maxwell-Boltzmann. And if you recall from the Maxwell-Boltzmann distribution of speeds, if we look at the population or fraction of molecules in a collection versus their speed, we can see molecules with a low temperature or a large molecular mass have a very narrow distribution, a very tight distribution at a very low speed. And as the temperature increases, that speed increases and the distribution becomes wider. They become more chaotic. Additionally, we could get the same effect by holding the temperature constant and changing the molecular mass by changing the identity of the gas. And we can see a low molecular mass molecule, so a light molecule, will be quite fast and have a large distribution of velocities. So recall that's what those equations looked like right here, okay? And remember, we developed two of these, one in which we use the mass in units of kilogram per molecule, which means we use Boltzmann's constant. And the other form of the equation we developed is when mass is in kilograms per mole, and thus we use the ideal gas constant. And recall from this Maxwell-Boltzmann distribution, we came up with a number of ways to describe their velocities. So we have the most probable, we have the root mean square, or we have the mean. Okay? So if we continue along with that and look at these postulates number 2 and 3, the size of the molecules is negligible. We can start to do some calculations to prove if that's true. So we start this by putting molecules into some type of tube that will allow them to have a successful collision. So we'll define the length of this tube with Greek letter lambda, which we refer to as the mean free path. So mean free path has Greek letter lambda, and that is the average distance a molecule will travel before colliding with another molecule. So in this tube right here, we have two molecules where their radii are indicated, and this sigma value right here, pi d squared, this represents our collisional cross section. Okay, so it is an area defined that will give us a successful collision. So now this distance d, I realize I mislabeled that. This distance d technically refers to the radius of this cross-sectional tube, right? The area of a circle is pi r squared. So think of this d as the radius of this collisional tube. And at a minimum, we need this distance d to be the radius of one atom plus the radius of another atom. That would give us like I should say that would give us the maximum distance they could be apart to get a successful collision. Okay. We also have to consider the mean relative speed between molecules. So that REL means relative. Okay. And an example of this is we can imagine in this tube where we place two molecules trying to get into a successful collision, they might actually have the same orientation, and thus their relative velocity will be 0, right? They'll never catch up with each other. If we put them on a head-on collision course, their relative velocity will be 2 times the velocity of each individual one, right? And if they're at some like 90-degree angle, that's given to us by Pythagoras, so their relative speeds would be √2 times their individual speeds. So there will be a great number of orientations of collisions that happen in this tube. And so we use this 90-degree to represent some average orientation. Okay? So I'm not going to go through these derivations, but we will later on in the semester. And what we would come up with for the mean free path is the following equation. And at 1 ATM, so I'll say at 1 ATM and about 298 K, this is roughly 65 nanometers. So a molecule will travel on average about 65 nanometers before colliding with another molecule. We can also calculate their collisional frequency. So that's what this term is. Collisional frequency. And using that relative speed as well as the collisional cross-section, and considering also at 1 ATM and roughly 298 K, this gives us roughly 7 times 10 to the 9, 1/seconds becomes this unit because it is a frequency. So in other words, molecules will travel about 65 nanometers before colliding with another one, and that will happen about 7 billion times per second. Okay? So when we say there's a brief interaction, we mean just that, right? 7 billion of these collisions per second. So each one individually is very, very short. And additionally, because the mean free path is 65 nanometers and molecular diameters are on the order of picometers, right, or angstrom, we can say that this actually works out pretty good as well. So both of these work as pretty decent assumptions. And thus, these calculations that we come up with, like collisional frequency, mean free path, and even using the Maxwell-Boltzmann distribution, we've assumed ideal gas behavior to make these calculations, but they actually work really well, which is pretty cool. So now, when we start to consider other aspects of our gases, however, and particularly when they get outside of ideal gas regime, our calculations don't work so well. So we have to figure out a way to correct this ideal behavior for real behavior. And we'll be uncovering that in the following videos.